Hello everyone, this is DA from Academy. Today we are going to see an important property of the compact spaces, that is, the continuous image of a compact space is also compact. So let's start its proof. So let X be a compact space and we have a continuous function f from x to y, and also assume that this function f is surjective, that is, f of x is equal to y. So we have to show that this y is a compact space. So again we have two things in total. The very first thing is that we have a compact space S, and second thing that we have a continuous surjective function f from x to y, that is f of x is y. And our target is to show that y is a compact space. So by using the two things, we will prove that y is a compact space. So now assume that we have a cover of y. So this is a cover of y that covers y in such a way that union of all of the v alphas equals to y. So this will be an open cover, and because f is a continuous function, so this v alpha, all of the v alphas that are the open cover of y have an inverse images in x and must also be open, because the continuous function says that the inverse image of an open set of an open cover is open. So the inverse images will denoted by u alpha is an x and will also be an open cover of x, because as v alpha is the open cover of y and covers y as the definition says, so the inverse image of the open cover in x, that u alphas in this, also covers x. So why this x covers by all of the u alphas? Because y is said to be a surjective function and it's also a continuous function, so that's why this u alpha covers whole of the x. And we know that x is a compact space, so there must be a finite subcover, that is, x is the union of some of the finite elements of the ui's from 1 to n, because x is compact space. So the really step is to recall the property that of the images of the function and the union of the images of the function. That is, the property is that image of the union of sets is a subset of image, the union of the individual images. So now we have a set x, or we have sets u alpha 1, u alpha 2, we can also write it as. So we'll apply this property on this set, like that is union of all of the u alpha 1, u alpha 2, u alpha n is a subset of the individual images, the image of u alpha 1 and union image of u alpha 2 and so on to the images of the u alpha n. So as x is the union of all of the u alpha I, so we can write all of this as f of x, and all of the other u alpha 1 union u alpha 2 is at union of all of u alphas I, where alpha from 1 to n. And what is u alpha? All of these u alpha i's are the inverse images of v alphas, so we can also write it as f of f inverse of v alpha i's, where union vary from 1 to n. So this will cancel out each other and eventually equals the union of v alpha I, where from 1 to n alphas go. So, and this is by definition is a subset of f of x, because f of x is y. Now we can write it as f of x is a subset of. So now we have that f of x is a subset of v alpha I, where alpha goes from 1 to n, and that is a subset of f of x by definition. So this thing happens if, then we can say that the union of alpha from 1 to n v alpha I must be equals to f of x, that is y. So because this is the finite subcover of a subcover V alpha. So if y equals to the union of the finite subcover, so this thing implies that y is indeed a compact space. So this thing implies that the continuous image of a compact space is compact, and this completes the proof. So this is for now. You're looking for more such videos, and you can subscribe this channel in order to watch my upcoming videos. We will meet in the next video. Till then, take care. Goodbye.